Hey, gang. So, what we're going to do here is look at rotational dynamics. So this is quite a bit different than linear, and let me show you why. So if I had this person, pushing this wheelchair bike, how you would solve this problem before is we would say we just took everything and made it a box, and we would say, okay, we have this force here, and then we would say, okay, F net equals MA and F equals MA and kind of move from there. But with torques or rotation, we have to completely change this now. And we cannot put the force there. So with torques, it's torque net equals I alpha. You guys have already learned about torques, so we have that. You have also learned about angular acceleration, so we're there. So today we're going to have to talk about this. And we'll see that here in a second. And so one thing we'll have to learn is you have to put the force at the location that it matters for rotation. Because if I put it at the center, you would know that it does not create any torque. So the location really matters. So let's take a look here at some different things. All right, added this in here. So this is the difference. For forces, we have F net equals MA. For rotational, we have torque net equals I alpha. So this is the difference we're going to need to talk about today, is that mass is also called inertia. So rotational mass is called rotational inertia, or I, or moment of inertia. So there's an equation, and I'll show you guys what that is here in just a second. But let's start with this for a point particle. So it's kind of like if you had a string and you were just spinning a mass around on that string. So just this one object. So torque net equals I alpha. So on this one, remember torque is force perpendicular to R, and this equals I alpha. Then we could merge together alpha times R, or angular times R, equals linear. So then linear, alpha would equal A over R. So this here is going to be A over R. So what I'm doing here is I'm trying to find I in linear terms that we've seen before. So then also we know force could be defined as F equals M times A. So I have that times R equals I. Then a little bit of algebra, I could multiply by R to both sides, divide by A to both sides. So I'm left with I equals mr squared for a point particle. So how do you find moment of inertia? And it just is mr squared. So things will have more rotational mass if they have more mass. Well, that's pretty easy. Then this also says they will have more rotational mass, which is I, if they have a greater r. That is not radius, but that is their distance from their axis of rotation, so how far that piece is. And so something that is farther away is harder to rotate than something that is closer together. So that's kind of why we went back to this, that right here, if I'm pushing here, this is going to be easier to rotate than the outer portion, because this mass is if I looked at that, I equals mr squared, excuse me, that inner red loop has a smaller r. It's closer to the axis of rotation, so it's going to be easier to rotate. And then we'll start to look into all objects, but all objects then play off of this. And really, to find the I of a system, you just add up. So then it's essentially you do the summation of all of your I's, or you could essentially say the I net. So I would just add up all the different pieces. So essentially what a disk here is if I thought about it as a long string of just a whole bunch of different masses. So maybe I have this little piece of mass at that distance. And then I have this little piece of mass a little bit closer, and this little piece of mass closer together. And then I would just continue to add it up for all of the masses, but that's what I'm looking at. So let's look at a couple here and try and do an example. So we want to do the eye of a system. And so two small weights are mounted. Calculate the moment of inertia of these two systems. So I of the system equals I net. So this is my axis of rotation. This is my R for that one. And this is my R. So for this first system, A, I would do I of the 5 plus I of the 7 equals I of my system. So then this is M5 R5 squared plus M7 R7 squared equals I of my system. So let's see, this is going to be 5 kilograms times R, which is 4 squared meters squared, and that's the correct unit. The unit for I is in kilograms times meters squared, plus 7 kilograms times its R. Oops, excuse me, that is not 4. That is from the axis of rotation. That's here. That is 2 squared times 2 meters squared. So that looks like 20, and 7 times 4, 28. So that is 48 kilograms times meters squared for A, right here, for this setup. So now let's look at B. Right? So B, that 5 kilogram, is now closer to the axis of rotation because what we're doing here is we're now gripping it closer. And then the 7 is farther out. So let's see what happens here. So I of the 5, that would be 5 kilograms, and it is 1/2 or 0.5 meters away squared, plus the 7 kilograms, and that is 4.5 meters away. So with this one, we're going to look at 5 times 1/4, so 5 over 4 kilograms times meters squared plus 7. Let's see, that's, I have a calculator present. 7 times 4.5 squared, and that is 140. I'm just going to round, 142. So this is much larger. B has way more, 142 plus something versus 48. So how could we logic that out and maybe not even have to do math? Well, if we see that I is just mr squared, conceptually, it just matters for the mass and how far that mass is. So both of these masses are pretty close. But here, the 7 kilogram is much farther away. If I have mass that is farther away, it is going to be a lot harder to rotate. And so that's what you want to be able to do, is talk about conceptually things that are harder to rotate or not. Most likely, we're not going to have to calculate this, but they'll ask us questions. These will be given, but they may ask us, maybe a student A says, I think a hoop is harder to rotate than a cylinder, and my moment of inertia proves that. But let's talk about it. So this says the moment of inertia of a hoop is mr squared, and a cylinder is 1/2 mr squared. Okay? Well, mr squared is greater than 1/2 mr squared. And so let's talk about that. Why is a hoop harder to rotate, right? It has more I because it doesn't have the 1/2 in front of it. So why is a hoop harder to rotate? Well, if I was going to look at this, the hoop, all of the mass is at the radius. Where if I were to look at this, only some of that mass is in this outer ring. Then all the other mass is getting closer and closer and closer, so that internal mass is very easy to rotate. And so these are the types of things you have to be able to do, is walk through what's harder and easier to rotate. So what about a rod? Is it easier to rotate a rod when you hold it in the middle and spin it? And again, you can take your pen and try to do that. So is it easier to spin it like that? Or is it easier to spin it when the mass is on the end? Right? And so what this tells us is this is 1/12 ml squared. So that one is easier to rotate versus this one is 1/3. And the reason is because this mass, okay, I get half of the rod is only half the length away, the maximum here. Where here I have some of the rod that is the entire length away. So if the mass is farther from the axis of rotation, it is going to be harder to rotate. And so again, that gets us to here. This is the really important stuff, is what's important about I, or moment of inertia. Okay? It depends on the mass and its distribution around an axis of rotation. It's no longer just mass. Right? It depends on where your axis of rotation is. And again, you don't have to be rotating to have a rotational inertia. They can ask you things about an object that's at rest and just talk about its rotational inertia. Conceptually, I like to think about it as something that takes more energy, or it's harder for you to rotate if it has more I, or rotational inertia. So from now on, we got to be careful. We cannot assume all mass acts at center of mass, because here we talked about a rod, and so if we were talking about rotating that, some of the mass is out here, some of the mass is here, and some of the mass is here. So it does depend on that distribution of mass of how that thing is going to rotate. So we'll get into some examples about that. Let me show you one here. So let's take a look at this. So here I have a ring stand, and so it depends on where I hold it. So if I hold it out here, all the mass is right here. Now for forces, it doesn't matter, because for forces I push up. Okay, that was pretty easy. If I go to here for forces, all right, that has not changed. And if I go to here, so if there's no rotation, it's all the same. But if I want to rotate it now, it does depend on where the mass is distributed. So here, all the mass is at the end. My axis of rotation is here. And so let's see. So I'm going to try and go up 90 degrees and back 5 times and see which one's easier to rotate. And maybe here, I'll get my phone out and I'll do a quick time, or maybe you guys could. And let's see what happens with this time. So, all right, 1, 2, 3, 4, 5. Oh, all right, that took me 7 seconds. Now let me try it again, but I'm going to change how the mass is distributed. It's going to be close to the axis of rotation. So my R value is now much smaller. And let's see how fast I can do this one. Okay, 1, 2, 3, 4, 5. Ooh. Okay, 4 seconds. So much easier to rotate when the mass is closer to the axis of rotation. So those are some examples that we'll be looking at. Here's our last few examples that we want to walk through before you have to do some on your own with these problems. So, in this example, it talks about these jacks type figures, and it says they're all the same distance, and then it tells me that the brass are shaded and the aluminum are less than the brass, and they're unshaded. So brass is a solid, has more mass. Okay? So all that matters is the mass and how far it is from the axis of rotation. So I know they're all the same distance, so I don't need to really focus on that. All I need to think about is which ones have more mass. And so here, this one has 1, 2, 3, 4 of the, lighter shaded, so it has less mass. These ones are pretty much right at the axis of rotation, so those ones are irrelevant because we're not really rotating about those. They're so close to the axis of rotation that R is 0. Here I have 2 shaded ones outside, Here I have two shaded ones that I would have to spin, and here I have 1, 2, 3, 4 shaded ones that I would have to spin. So the harder ones to spin are going to be more inertia. So my ranking for this one would be D, B equals C is greater than A. And so I could talk about I, or moment of inertia, depends on mass and how far it is from the axis of rotation. And let's be careful using the word it. How far the mass is from our axis of rotation. D has more mass farther from axis of rotation. And then the ranking follows that pattern. All right, let's take a look at this one. Maybe you want to pause it and try it on your own before I go and do this one. So all three segments are equal length, and then they have different masses. The moment of inertia will be greater on the left, right, or same on both. So let's think about it. If I held it here, right? This has a small mass. That small, let's call that length. This mass is at this length, and this mass is out at this length. Okay? So remember, I, again, equals mr squared. We're not actually going to calculate it, but let's just think conceptually. I notice I have more mass, the 3m, at a greater distance. Okay, when I hold it there. If I hold it on the other side. Now that 3m is a lot closer. The 2m is there, and the singular m is there. So they are definitely not the same. There is more inertia when I'm at the left end. Okay? So when holding it left end, there is more mass farther from axis of rotation, so more rotational inertia. Again, I'm trying to go fast for the video's sake, but to have something down there for you guys to see. But make sure you're having proper handwriting when you're doing that, or typing may be a good option for you on our test. So I think we're down to our last example here. So again, try pausing it and thinking what you have. So let's rank these. Again, we have a chart it may give us, or they just may ask you to do it and explain it, again, knowing I equals mr squared. That's an expectation. So it tells us they have the same mass and the same radius. So if we think about this one, the ring is always going to be the hardest to rotate because the ring has all the mass at the radius. A cylinder essentially doesn't have all the mass. Now you may go back and see, but a cylinder I know is 1/2 mr squared. So essentially it's saying this cylinder is the equivalent of when you add up all the mass, that all the mass is at half the radius, is how you could look at it. Or you could say what percentage of the mass is at the radius. So for a cylinder, only half of the mass acts at the radius, is how that could be looked at. So again, this one has all the mass at this radius, so it's farther away from the axis of rotation, where this only has some. So let's talk about then if we remove it. So some people may want to say, well, these are both rings, so they'll be the same. But let's go back and think to this problem. This problem, right, do you notice how I have a ring right here? Yeah. So this ring right here is not the same mass as this one, because these two pieces, okay, so pieces 1 plus piece 2 equals the mass of piece 3, because it told us this mass of 1 equals this mass of 2. So when I take those two parts away, they have to equal this one. So again, the greatest one is this is going to be first, right? Because it has all of the mass and the most mass at the center. Then this one we really don't know where it's divided out, but typically we would just talk about if it's on the outside, it's going to be a greater rotational inertia, and this would be 3. Right? So that's our examples of rotational inertia. Right? Make sure you practice those, and then you'll be able to see some other problems on how to use rotational dynamics once you know that I value.